Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to show that correlation does not generally imply causation. First, we will show that under certain circumstances, correlation can reflect causal relationships between variables. But then we will show that confounding factors can easily produce spurious correlations between variables that are not causally connected. We will illustrate this with a simulated dataset and also with a real-world dataset. Let's get to it. We're going to show that correlation usually does not imply causation, but sometimes it can. Here is a dataset showing monthly data from Spain between 2015 and 2022. On the y-axis, we see the unemployment in millions, and on the x-axis, we see the temperature. For example, here this month, the mean temperature was 60 degrees Fahrenheit and the unemployment was 3 million. We immediately observe that when the temperature is high, the unemployment tends to be low, and when the temperature is low, the unemployment tends to be high on average. In fact, the correlation coefficient between the two variables is negative, indicating a negative correlation that we clearly see in the scatter plot, and it's equal to minus 0.21. So it's pretty substantial. Now the question that we would ask as economists would be, would an increase in temperature actually decrease unemployment? If for whatever reason next month we see in the forecast that the mean temperature is going to be abnormally high, does this mean that we can expect lower unemployment because of that? If you think about it for a moment, probably you see that common sense dictates that that will not be the case, but we're going to explore this type of questions rigorously from the lens of causal inference. So in causal inference, the key question tends to be whether a variable that we call the treatment causes changes in another variable that we call the outcome. Notice that here we're using outcome with a different meaning than when we're talking about probability spaces. In previous videos, we have tackled this question when the treatment was binary. But here, we're going to consider cases where the treatment can have many variables. In fact, in our example, the treatment is the temperature because we want to see whether a change in temperature produces a change in the unemployment. So the unemployment here would be our outcome of interest. In order to explore this type of questions rigorously, we introduce the potential outcomes. Potential outcomes are a family of random variables that depend on the value of the treatment. So this tells us what the distribution of the outcome of interest is when the treatment is equal to a particular value. And what we have to understand here is that the potential outcomes for the different treatments are always defined even if we don't observe that value of the treatment. So they're defined both for the observed treatment, but also for alternative unobserved values of the treatment. I'll explain what I mean a little bit more precisely now with an example. The observed data is equal to the potential outcome, It's equal to the potential outcome for the value of the treatment that is actually observed. So here, this means that the treatment was equal to that particular constant. Remember that we write random variables with a squiggly line on top. So this guy is a random variable. And we write constants or deterministic variables without the squiggly line on top. So by this we mean that the random variable representing the treatment, in our example, the temperature is equal to a particular value. For example, 40, okay? And when that happens, the data is equal to the potential outcome corresponding to 40. So that we're going to observe, but the other potential outcomes are also defined. The potential outcome for 30, 45, 63, 75, they're all defined, but we don't actually observe them in the data. They are counterfactuals because they're counter to factual reality. And that is the fundamental problem of causal inference. We have incomplete data. If we manage to observe our outcome for every possible value of the treatment, if we had access to the unemployment for, let's say, last month when the temperature was 50 degrees, 60 degrees, 70 degrees, every possible temperature, then we would clearly know whether the treatment, in this case the temperature, was having a causal effect on the outcome. However, we're only going to be able to observe the outcome for one specific value of the treatment for each data point. In the case of last month, whatever the mean temperature last month was. If it was 40 degrees, we're going to observe the potential outcome corresponding to 40. We're not going to observe everything else. And that is the fundamental problem of causal inference. That is why causal inference is a very, very tough problem. Here is a picture. Imagine that a treatment has no causal effect on a potential outcome. So here I'm showing you the value of the potential outcome associated with every possible value of the treatment, and you can see that it doesn't change. But the problem is that we actually don't see that from the data. From the data, we only see the potential outcome associated to a specific value of the treatment, which is the value that actually occurred. Again, if you think of the unemployment and the temperature is only equal to a particular value, let's say 40 here, and we're only going to observe the unemployment corresponding to that value of the temperature. In fact, here because this is a simulated example, well, a synthetic example that I made up, we know that the potential outcome does not depend on the treatment, but it could have equally well been like this. In this case, more treatment, like higher value of the treatment, corresponds to a higher value of the potential outcome, but we don't know because we only see one data point. Of course, we always measure more data points, but here we obtain not only a new realization of the treatment, we also obtain different realizations of the potential outcomes. So this is the new value of the potential outcome that we observe. Here there's still no causal relationship because we see that if the treatment had been equal to other values, the potential outcome would have been the same. So there's no causal effect. But again, it might be tough to figure that out because we only observe one value of the potential outcome. Here again, we see another value of the potential outcome. The potential outcome again would not have changed for other values of the treatment, but we only get to see that data point. From these three data points that we saw, this is what the whole data set would look like. And from this, we would try to figure out whether there's a causal relationship between the treatment and the observed outcome. So hopefully this illustrates for you the fundamental problem of causal inference, where we actually observe this, but what we would really have wanted to observe is this. We would have shown us the different potential outcomes for different possible values of the treatment for each data point. Unfortunately, we only get to see one. In the case of temperature unemployment, for each data point, we will see one value of unemployment corresponding to the observed temperature. We don't get to see what the unemployment would have been if the temperature would have been 5 degrees higher, 5 degrees lower, etc. And that is why, again, causal inference is very tough. Here, we're going to focus on linear causal effects between variables. We're going to ask the following question. If the potential outcome is modified by the treatment, and it's modified in the following way, linearly, where there's a constant that determines how much the mean of the potential outcome changes when we change the treatment, then can we identify this linear effect? So in the case of the unemployment and the temperature, this would mean that if we change the temperature by 1 degree, then the unemployment would change by beta. The mean of the unemployment would change by beta. The key question here is, can we estimate such linear causal effects from data? And a natural way to try to quantify linear effects that act on the outcome on average is the covariance, or equivalently the correlation between the two variables, because as we have seen in previous videos, covariance and correlation quantify the average linear relationship between two variables. So it is natural to just compute the covariance between the observed outcome, which we call y, and the treatment t. Here we're going to at first make the following assumptions. The treatment is not chosen according to the potential outcomes. It's independent from the potential outcomes. We'll see that if this is true, then correlation or covariance does capture causation. But then we will discuss why this is actually difficult to achieve. And we will also illustrate what it means for the treatment to be independent from the potential outcomes, because this can be confusing the first time that you see it. Perhaps in a nutshell, this basically just means that we don't choose the treatment according to what the potential outcomes are. Typically, we achieve this by randomizing the treatment and just picking it at random so that this renders it independent from the potential outcomes automatically. Okay, but first let's see the implications of independence, and then we'll discuss why independence is important and why it's difficult to achieve. So to simplify our computations, we're going to assume that we have standardized the treatment. We have removed its mean and we have divided by its standard deviation so that its variance and its mean square are equal to 1. Now, if we consider the covariance between the observed outcome and the treatment, it's just equal to the mean of the product because this guy is 0. And now, if we apply iterated expectation, I was going to say linearity of expectation, we will apply linearity of expectation later on in the video. Now we're going to apply iterated expectation. So this object is the conditional mean function of the random variable yt. If you're confused, you can just think of the conditional mean function of a random variable b that is equal to y times t, okay, conditioned on t. An iterated expectation tells us that if we take the mean of the conditional mean function where we input the variable that we condition on, then we get the mean of this guy, which is what we want. You want to review this, you can take a look at the video on the conditional mean and iterated expectation. All right, so what does the conditional mean function of this random variable that I was calling b, but is equal to y times t, equal to when we condition on t? Well, by definition, it's here I'm assuming that the outcome is continuous. If it was discrete, this would just be a sum. We basically compute the mean of this quantity, but we use the density that is the conditional density of y given t. Okay, notice that if we're conditioning on the treatment being equal to a certain value t, then this is going to immediately fix this guy. All right. Now, remember that if we observe that the treatment has a certain value, then the observed outcome is equal to the potential outcome associated with that value. This is why here we're replacing y by the potential outcome associated to this constant t that we're observing. Now realize that we can take this guy out because it's constant with respect to the outcome. And here we can use the fact that we are assuming, and this in general will not hold, which is why correlation does not imply causation, but here we're assuming that it holds to show you that under those circumstances, correlation does imply causation. Here, because of the independence, we can replace the conditional PDF of the potential outcome given the treatment by just the PDF of the potential outcome. And now you might be confused here because you have a y, but y is just a variable here. You could replace it by any value, by a, b, or whatever. You will realize, if you do that, that all of this is just the mean of the potential outcome. So in general, the conditional mean function when we fix the treatment to be equal to t is just equal to t multiplied by the mean associated with that potential outcome that depends, that the mean of the potential outcome associated with t, with that value of the treatment. Now we can go ahead and take this conditional mean function and plug it in here, but we have to plug in the random variable that represents the treatment. in order to apply iterated expectations so that we get the covariance. If we do that, oh, and I forgot to, of course, I went into this, long reasoning before realizing that first we should input the fact that this guy is equal to beta t by assumption, because we assume that t looks horrible. There is a linear relationship between the treatment and the potential outcome. So the conditional mean function is equal to beta times t squared. Now we're going to input this guy here, replacing the constant t by the random variable representing the treatment. And if we do that, here we get the mean of beta times t squared. The beta can come out by linearity of expectation, and this guy is just equal to 1 because we have standardized the treatment. So the covariance is equal to this coefficient that exactly characterizes the causal relationship between the treatment and the potential outcome. But this only works if we have independence. If we can do this step here where we're replacing the conditional density by the marginal density of the potential outcome. So why is independence so important? Well, independence means that we don't choose the treatment according to the potential outcome. Look at this example. Here in this example, when the potential outcome is high, we apply a larger treatment. And when the potential outcome is low, we apply a smaller treatment. Notice that here we could easily have applied this treatment and we would have obtained the same outcome, because for this example, the potential outcome does not depend on the treatment. But because we did this, for large potential outcomes, we chose large treatments, and for small potential outcomes, we chose small treatments. We have induced spurious correlation between the treatment and the potential outcome that is obvious when we actually observe the data. So here it seems that when the treatment is small, the potential outcome is small, and it looks like when the treatment is large, the outcome is large, but this only happens because we chose the treatment in this way. Okay? This is like giving a medicine to the healthy people and then saying that the medicine works. If we have independence between the potential outcomes and the treatment, then you cannot choose the treatment in order to fool us. Basically, the treatment would have been, randomly chosen anyway here, and here, and it would have been highly unlikely that you could produce that spurious correlation in this case where the potential outcome does not depend on the treatment. You can achieve that by randomizing the treatment, not looking at anything else, just generating it at random every time. In order to illustrate all of this a little bit more in detail, we're going to look at an example which I made up where there's this guinea pig rescue. Okay, and the guinea pigs are too thin, and the rescue personnel want to fatten them up. So they decide to try a nutritional supplement that is supposed to help guinea pigs gain weight. In this picture, you can see the supplement here. So during the first week, the personnel put the supplement mix in with the food, and they keep track of how much supplement each guinea pig eats. And at the end of the week, they measure the weight of the guinea pigs and they see whether they have gained or lost weight. This is the weight change in the guinea pigs, and this is the supplement intake. Everything is standardized, which is why you see negative values for the supplement intake in case you're wondering. And what the people in this guinea pig rescue see is that the guinea pigs that are eating more supplement gain more weight, and the guinea pigs that are eating less supplement gain less weight. So they say, it looks like the supplement is working. But just in case, they continue and the covariance is 0.8. So there's very strong correlation between the supplement intake and the weight change. If the quantity of supplement that was fed to each guinea pig was independent from the potential outcomes associated with the weight change, not the observed outcomes. Oops, sorry about that. Not the observed outcomes, the potential outcomes. I got a bit excited there. If that were true, then according to our derivations, then this covariance would reflect a causal relationship between the supplement and the weight change. We could conclude that the supplement works. But right now, we don't have that guarantee. So the second week, the person in charge of the guinea pig changes, and they decide to feed them the supplement after they have eaten their food. And they still keep track of how much supplement each guinea pig eats and what their weight change is. And lo and behold, they observe the completely opposite pattern. Here we see that the guinea pigs that are eating more supplement gain less weight, and the guinea pigs that eat less supplement gain more weight. So what is going on here? The covariance is minus 0.8. There's a strong negative correlation between the supplement and the weight of the guinea pig. So it looks like the supplement is actually hindering the guinea pigs from gaining weight instead of helping them to gain weight. So the people in the guinea pig rescue are very, very confused. So what's going on? What's going on is that the treatment here depends on the food intake. Why? Because when the guinea pigs are fed the supplement mixed in with the food, the ones that eat more food eat more supplement. When they are fed the supplement after the food, the ones that have eaten more food eat less supplement. And here, food intake is actually very dependent on the potential outcomes. The guinea pigs that eat more food gain more weight. And this induces a connection between the supplement and the weight change that goes through food intake. So it's not that the treatment is causing the weight change, it's that the treatment, in this case the supplement, is associated in different ways with food intake, which does cause, which is causally connected with the weight change. In the language of in this formal language that we're using before, the treatment is now dependent on the potential outcomes. For example, when we're giving the supplement mixed in with the food, we're giving more supplement to guinea pigs that are going to gain more weight change regardless. So this induces a dependence between the potential outcomes and the treatment, and because of this, we cannot trust the correlation that we see in the data. So how can we break the dependence between these potential outcomes at the treatment? We have to avoid giving systematically more supplement to guinea pigs that are systematically going to gain more weight or systematically less weight. Well, we can achieve this by randomizing the supplement provided to each pig. This, of course, would be extremely annoying to do, but you could do it, right? You could have like a random number generator, and according to that, you would give different quantities of supplement to each pig, and then you would have to make sure that they actually eat it. So in our simulated scenario, this actually happens, and what happens then? Well, we see that the supplement actually has zero correlation with the weight change. Now, this spurious correlation that arises because of the connection between the supplement and the food intake is no longer there because we're randomizing the supplement, and that breaks its dependence with the food intake, and this enables us to discover the true causal relationship between the supplement and the weight change, which is that there's no causal relationship. The supplement does not work. So let's analyze this a little bit more in detail, in particular the role of the food intake. Here, the potential outcomes depend on the treatment T, but they also depend on something else, which we call a confounder. In our example, this was an unobserved confounder because the personnel had not realized that food intake was the main driver of weight change in the guinea pigs and that it was connected with the amount of supplement that they were taking. We're going to analyze this with a simple model where there's a linear relationship between the potential outcome associated with a certain value T of the treatment and that value T, and it's dictated by this coefficient beta treat This is what we would like to find out. This tells us the linear relationship between the treatment and the potential outcome. In the case of the guinea pigs, between the amount of supplement they eat and their weight change. But there's also a confounder C that can be dependent on the treatment, okay, and that is multiplied by another constant beta confounder. And apart from that, we can also have some additive variable here that is not dependent on anything. It's just random noise, which kind of reflects other quantities that could have an effect on the potential outcome, but are uncorrelated with the treatment and the confounder. What do we actually observe? We observe this quantity, but for the value of the treatment that actually occurs. Okay, remember that random variable t reflects the treatment that we actually get to observe. And, oops, sorry, today I'm dropping everything. And that immediately determines the value of the observed outcome y, which is what our data. When we're sampling our data, we're sampling from y. So what are the assumptions here? Just to recap, T and C are going to be standardized just to simplify the calculations. This is not too important. You can always standardize your variables. And C is independent from the treatment and from the confounder. Okay, this additional value there. Okay, so now let's take a look at what happens when this linear model actually holds. Of course, this is an idealized model, but it's useful to see how confounders can have an effect on the observed correlation between two variables of interest. When that idealized model holds, what is the covariance between the observed outcome and the treatment? Because the treatment has zero mean, the covariance is just equal to the mean of the product. And now we're going to plug in here the value of the observed outcome, which is beta treat times t plus beta conf times c plus z. Okay? And here we're going to apply linearity of expectation. The constants come out. Okay, and the random stuff stays in. We have standardized the treatment, so this is going to be equal to 1. Here we have the covariance between the confounder and the treatment, because again the treatment is equal to has zero mean, and these guys are independent. This is why we have split up the mean of the product into the product of the means, and this guy has zero mean. So that term is going to disappear. And what we're left with is the coefficient that we are after, so that's the good news. But we also have an additional value, an additional quantity that is equal to the coefficient multiplying the confounder, which just shows how strongly the confounder affects the potential outcomes, and the correlation between the treatment and the confounder. So the covariance is distorted by the confounder. Look at this. If we want to see under what situations the covariance actually reflects the true causal effect, well, either when this is zero, which means that the confounder does not affect the potential outcome. In our case, that would mean that the food intake would not affect the weight change, or the covariance between the confounder and the treatment is zero. In our case, that would mean that we have randomized the amount of supplement that we give to the guinea pig so that it's uncorrelated with their food intake. If that happens, this indeed is zero, and we get to see the true causal linear relationship between the treatment and the outcome, as we had proved previously. So it's good to see that this still holds for our idealized model. So now let's take a look at our specific example for these guinea pigs. In our specific example, the potential outcome is the weight change, and the weight change truly does not depend on the supplement. So here it only depends on the food intake, which is the confounder, and some other variables. For example, the genetics of the guinea pig or something like that. And so what we get to observe is just the value of the confounder plus these other random quantities. the treatment is the supplement intake and it doesn't work. So the causal relationship that we're trying to find out is actually a coefficient equal to 0. The food intake does affect the potential outcomes. In this case, I decided to make things simple to just set this coefficient equal to 1. So now what is the covariance between the observed weight change and the supplement, which again we would like to be equal to 0 so that we could correctly identify the causal relationship between the supplement and the weight change? Well, by our formula that we had just derived, is equal to beta treat plus beta conf times the covariance between the treatment and the confounder. In this case, this guy is 0 and this guy is 1. So we had to observe the covariance between the treatment and the confounder. If that covariance is non-zero, we're not going to see the true causal linear relationship between the supplement and the weight change. And in fact, that's what happens when we give the guinea pigs the supplement mixed with the food. The covariance between the food intake and the amount of supplement that they eat is 0.8, and you see it here. So the pigs that eat more supplement, they eat more food. And the pigs that eat less supplement, they eat less food. And because of that, the covariance between the observed outcome and the treatment is equal to that covariance between the confounder and the potential outcomes, as we proved in the previous slide. So then the guinea pigs that are eating more supplement, they gain more weight, but that happens because their food intake is larger. And we can see this because I have color-coded the food intake for each of the guinea pigs, and we see that those that are gaining more weight, it's not because they're eating more supplement, it's because they're eating more food. Similarly, the ones that are not gaining weight, it's not because the supplement is small, it's because they're eating less food. It's because of the confounder. Again, in this idealized example where the supplement and the weight change are actually not causally connected. When the supplement is fed after the food, then there's a negative correlation between the supplement and the food intakes, because the guinea pigs that have eaten less food, they're hungrier, so they eat more supplement. And the guinea pigs that have eaten more food, they're less hungry and they eat less supplement. This negative covariance between the treatment and the confounder, in this case the supplement and the food intake, is reflected spuriously in the covariance between the observed outcome, which is the weight change, and the treatment, which is the supplement intake. So again, we observe that less supplement, more weight change, but this is because these guys are actually eating more food. And then we observe that more supplement, less weight change, and that is not because of the supplement, it's because they're eating less food. If we randomize, then we break the correlation between the treatment and the confounder. We break the correlation between the supplement intake and the food intake. The guinea pigs that are eating more supplement are not eating more food systematically or less food systematically. We see this is pretty clear from the scatter plot. The covariance is 0. So as a result, it doesn't happen that these guinea pigs that are eating more food are eating more or less supplement, again, systematically. So hence we observe a 0 correlation between the weight change and the supplement as we would want to. And this reflects the fact that the supplement and the weight change are not causally related. But this is only because we managed to randomize the treatment so that it was independent of the confounding factor. Now let's go back to a real data set of monthly data in Spain, where we saw that there's a negative correlation between temperature and unemployment. So common sense tells us that if next month the forecast is that the temperature is going to be several degrees higher, that will not be reflected in the unemployment being the unemployment being lower. What could be the confounder here between unemployment and temperature? Maybe stop the video and think about it for a moment. The confounder here is the number of tourists. So when the temperature is high, the number of tourists is high, and this is why we see less unemployment. And when the temperature is low, then we see less tourists, and that's why we see more unemployment. If next month suddenly more tourists were to come to Spain, then there would be more people working, there will be less unemployment. So here we see that in real-world datasets, it's also very easy for confounding factors to produce spurious correlations between two quantities, such as unemployment and temperature, that are not causally connected. All right, so what have we learned? We have learned that correlation does not imply causation, but it can if the treatment is randomized to break its correlation with any possible confounding factor. Otherwise, unobserved confounders can easily produce spurious correlations between quantities that are not causally related. And that's all I got. Thank you very much.